Hi, everyone. My name is Wentao Huang. I graduated from Renmin University of China. Today, I will present our paper at SIGIR 2020, BiANE, Bipartite Attributing Network Embedding. This is a joint work with my collaborators Yuchen Li and Yuan Fang from Singapore Management University, Hongxia Yang from Alibaba Group, and my supervisor Zhu Fan, who is also from Renmin University of China. So, we focus on the network embedding problem on the bipartite attributing network, which is a ubiquitous data structure to model many real-world scenarios. At first, let's have a look at the outline of this presentation. In the beginning, I will introduce the background and technical challenges of embedding bipartite attributing networks. Next, I will make a detailed elaboration of our proposed model BiANE. Then, I will present experiments conducted to evaluate the efficacy and efficiency of our model. In the end, I will conclude the contributions and point out some potential research directions to do in the future. First of all, let's start with the introduction part. Networks provide a ubiquitous way to organize a diverse set of real-world information. They have been utilized to model multiple disparate domains, and embedding techniques has become a powerful tool to study a network problem in both academic and industrial fields. Among all kinds of network structure, the bipartite attributing network is a common data structure to model. For example, an e-commerce website can be modeled as a bipartite attributing networks, where each node can be categorized into two distinct partitions, and edges only exist between nodes from different partitions. Moreover, each node is also affiliated with a set of attributes, which provide the auxiliary information besides the topology structure. Apart from this, bipartite attributing networks can also be applied to model other applications, like recommendation systems, biological community detection, finance risk assessment, and so on. However, such a network structure has long been ignored from the academic field. Little efforts have been exerted on embedding bipartite attributing networks. Some related works, like recommendation systems or inference diffusion models, can be employed to tackle this problem, but they only output a simple scalar as the final result, which fails to convey rich information like embedding vectors. To obtain embeddings, we can resort to existing embedding techniques. However, they are not sufficient to embed bipartite attributing networks, for they fail to extract some key characteristics of the network. In general, there are two key observations that lie at the core of bipartite attributing networks. First, we need to preserve the inter-partition proximity, which represents the interaction behaviors of the nodes. Besides this, we also need to preserve the intra-partition proximity of the network. To be more specific, the intra-partition proximity consists of the attribute proximity and the structure proximity, which are the proximity of two modality information. On the one hand, nodes with similar attributes tend to share similar interaction behaviors. For instance, Lisa and Alicia are both young ladies. Thus, they tend to spend money consuming cosmetics. On the other hand, nodes sharing common neighbors are supposed to have large high-order proximity, for they have similar interaction behaviors. Therefore, to effectively embed bipartite attributing networks, we need to preserve the information proximities. However, such observations bring about some technical challenges of embedding. First, the attribute information and the structure information are two different modalities. They provide complementary information for each other. Meanwhile, since they describe two aspects of the same node, these two information also share an underlying coherence. We refer to this relationship as the attribute structure correlation. It is the attribute structure correlation that existing methods cannot effectively capture. Neither shadow operations nor deeper models can capture this relationship. Therefore, how to preserve the attribute structure correlation could be a real problem. Another issue of embedding is about negative sampling. Most embedding methods adopt a static negative sampling strategy. However, as the training proceeds, A static negative sampling distribution cannot reflect the varying node information in an embedding space, which brings about noise in the training. Another solution is to adopt a dynamic sampling distribution, but most dynamic sampling strategy often cause great complexity. Usually, the complexity is big O(n) squared, which reduces the scalability of the model. Such issues are even exaggerated on bipartite attributed networks, since a typical strategy to model intra-partition proximity is to physically augment some edges inside each partition, which makes the sampling distribution update a heavy burden. Therefore, to effectively embed bipartite attributed networks, we need to overcome the affirmation technical difficulties. We now move on to elaborate on our model in detail. First, let's take a look at the overall framework of our model. Given a bipartite attributed network G, here U and V are two distinct node partitions, and curly Q letter E represent a set of edges across two partitions. SU and SV stand for the attribute set for partition U and V and respectively. We first synthesize an intra-partition network within each partition. If two nodes are linked to a same node in the other partition, we manually add a link between these two nodes, which are indicated as the dashed lines in the picture. The links can also be assigned some weights, like Jaccard similarity or inverse user frequency, based on their common neighbors. After that, we perform intra-partition proximity modeling inside each partition, and obtain embeddings for each node. Then, we preserve the inter-partition proximity with the obtained embeddings according to the edge relationship across two partitions. We now take a scholar publisher network as an example for better illustrations. In this network, nodes can be partitioned into scholars and publications, and edges across two partitions represent the authorship relation. Scholar nodes have attributes like research interest, gender, the affiliation information, etc., while publication nodes are affiliated with attributes like venues or abstracts. Let's take Professor Jiawei Han as an example. We first dig into each partition to model the intra-partition proximity. From the network, we can discover that Professor Han has some co-author relations with other scholars. We first calculate the k-step normalized transition probability inside the scholar partition according to this formula, which can help us obtain the high-order structural proximity for Professor Han. Meanwhile, we extract the attribute information from the attribute set for Professor Han as his attribute features. Then, we perform compact feature learning by feeding attribute features and structural features into two independent autoencoders and obtain two encodings S prime and Z prime respectively. Since neighbor nodes usually have larger similarity than distant nodes, we also perform joint modeling for attribute encodings and structure encodings simultaneously in this step, which aims to preserve the first-order proximity inside each partition. After this step, we move on to model the attribute structure correlation for the network. As we mentioned, the attributes information and structure information convey complementary information for each other. We ought to adopt some operation to model their underlying coherence. The main idea is that for each node itself, its attribute embedding is supposed to be correlated to its structure embedding. Last, we ought to preclose their embedding vectors in the embedding space. Here, we introduce two auxiliary transforming kernels to map the affirmation encodings into low-dimensional vectors in the embedding space. The reason for employing such kernels are twofold. First, we have performed joint modeling in the encoding spaces. If we directly preclose the attribute embedding and structure embedding in this space, we may make the affirmation training unstable. As for the second reason, we'll illustrate in the next slide when we introduce the sampling method. We now project S prime and Z prime to tilde S and tilde Z in the Latin space, and we preclose their distance by maximizing their dot product value in the Latin space. In the meantime, We also utilize negative sampling to push away the unrelated nodes in the embedding space. Thus, we can ensure that the attribute structure correlation can be well preserved. We now move on to the next part about sampling strategy. We have pointed out the shortcomings of existing static negative sampling and dynamic negative sampling. To overcome their limitations, we introduced a novel dynamic positive sampling strategy to ameliorate the training. In fact, the attribute structure correlation not only exists inside a single node, but also exists among different nodes if they are semantically related. Putting close the embeddings of related nodes can also enhance the attribute structure correlation. Therefore, we can utilize such relatedness to discover the potential positive cases for each node and update the sampling distribution by performing k-nearest neighbor search after each training run. To save the time complexity, we resort to HNSW for KN search. HNSW is an efficient method for KN search, and complexity is only big O n log n, which is far smaller than the square with a big O n square complexity for most dynamic negative sampling methods. However, such complexity can only be achieved for low-dimensional vectors. So we introduced the affirmation transforming kernels to reduce the embedding dimension to a smaller value. As the training proceeds, we perform HNSW-based KN search in the Latin space, finding potential positive nodes and pull close their embeddings. In the meantime, we also adopt static negative sampling to push away the negative nodes. Thus, each node may be subjected to two forces, as indicated in the top right figure. One positive force, which is represented as the solid line, to push it up, and the other negative nodes, as indicated in the dashed line, to knock it down. Every node can be knocked down by the negative nodes, but only the potential positive nodes can be pulled up. Through this means, we can update the sampling distribution and ameliorate the embedding training. Last, we move on to model the inter-partition proximity. We concatenate the attribute encoding and structure encoding from formation autoencoders to obtain the final embedding for each node. And we maximize the layer joining probability of nodes according to edges across two partitions to preserve the inter-partition proximity. We jointly model the inter-partition proximity and the intra-partition proximity. After training is converged, we can obtain the final embeddings. Now, we will move on to the experiment part. We conduct two typical tasks to evaluate our model: link prediction and node classification. The link prediction is measured in terms of AUC-RC and AUC-PR, while the node classification is measured in terms of macro F1 and micro F1. We use 3 real-world datasets for our experiments. The statistics of our datasets are listed in the table. Beyond that, we also report the sparsity of each dataset according to its formula. As for the baselines, we mainly compare with 3 types of embedding methods: homogeneous methods, heterogeneous methods, and attributed network methods, which are shown in this slide. For each baseline, we use the default implementation released by original authors, and we fairly tune hyperparameters for its optimal performance. Noticing that ANIL and AANE and FitWorks targets for embedding homogeneous attributed networks and have one encoder for node attributes only, we concatenate attributes from 2 partitions by padding them with 0 to a fixed length. The embedding dimension for all methods is set to 128 for a fair comparison. Let's first have a look at link prediction. We randomly hold out 70% links for training, and we use a remaining set for testing. After training, we train a logistic regression classifier to predict the probability of a link. As we can see from the table, our BiANE model achieves the best performance. This is due to that BiANE can effectively model the intra-partition proximity within each partition and capture the high-order structural relation of the network. This manner contributes to the outstanding performance of link prediction. As for the node classification, we randomly select 60% and 80% nodes to train a logistic regression and test the classifier performance of the rest of the nodes. As indicated in this table, BiANE also outperforms other models. The reason is that BiANE can effectively preserve attribute structure correlation, which can help to better integrate attributes information and extract rich features to embedded networks. We also make the ablation study to validate each part of our model. The experimental configuration is shown in this slide. It is worthwhile to point out that BiANE IS and BiANE ISL both replace the HNSW-based sampling with the importance sampling from list distribution, which brings about the complexity of a big O n squared. We report the node classification performance for the ablation studies. The best results are marked bold, and the second best is underlined. From the table, we can find out that utilizing both attribute information and structure information can improve the performance. And the intra-partition proximity modeling is a key step in embedding bipartite networks. From the last three rows, we can find that BiANE can reach similar performance as BiANE IS and BiANE ISL, which validates that our dynamic positive sampling strategy can bring about the same improvements as the affirmation importance sampling, but with smaller time complexities. We also investigate the sensitivity of the number of sampling cases. We vary the number of positive samples and negative samples from 0 to 100, and we conduct linear precision experiments or movie length datasets for evaluation. The horizontal axis represents the number of samples, and the vertical axis is the respective AUC value. The red line and the blue line stand for the performance of the model with varying positive samples and varying negative samples respectively. From these charts, we can find that a model with positive sampling outperforms a model with only negative sampling, and optimal performance can be achieved with a positive case around 5. Therefore, the experiments again support that positive sampling does enhance the model performance in addition to a negative sampling. After validating the efficacy of our model, we conduct some tests to evaluate the efficiency. In our experiments, the sampling part takes up most of the training times, so we only report the time cost of a single round of sampling to evaluate the efficiency of our model. We compare our HNSW-based sampling method with the affirmation importance sampling method, and we do experiments with different dimension vectors on networks of different scales. The results are shown in these charts. Each chart indicates the time cost of the sampling with a certain dimension vector. The horizontal axis represents the size of the network with different number of nodes, while the vertical axis is the overall time cost of a single round of sampling. From these charts, we can observe that HNSW-based sampling costs much less time than the affirmation importance sampling method. And such superiority is more obvious with the low dimension vectors, which proves the rationality that we reduce the vector dimension to a smaller value by employing the auxiliary transforming kernels. The importance sampling can even not finish a single round of sampling with a network of 10 million of nodes within the week, which again proves the efficiency of our model. At last, we make a conclusion. Our BiANE model can effectively embed bipartite attributed networks, for it is sufficient to model the intra-partition proximity and the inter-partition proximity. Also, the proposed novel dynamic sampling method improves the training process, which also makes our model scalable to large networks. For future work, we intend to reduce the space complexity for network embedding. And we also want to extend our work to embedding dynamic bipartite attributed networks. That's the end of my presentation. Thank you for watching this video.